Hello students, welcome to the lecture series on basic electronics, particularly in the first lecture of basic electronics. This series will be very much helpful for all those students who are recently admitted to the first year of engineering, particularly in the branch of electronics and communication, electronics engineering, computer science, information technology, as well as electrical engineering, because they will have to study the same subject in the first year, either in first sem or second sem. So in this particular introductory lecture, we will discuss all the basic aspects of electronics, its origin, its revolution, its current status, and which are the different fields which can be affected by electronics. So at the end of this lecture, you will be able to define various applications of electronics and what are the key features of electronics and which are the probable fields which can be affected by electronics. So we particularly want to go to the lecture session, which you can see on the screen. The title is Introduction to Electronics. So the first question arises is, what is electronics? So as you all were students of science field, so you must be knowing physics is the base of all engineering and technological branches, because all branches are called applied physics. So what is electronics then? It is the branch of science, or you can say physics and technology, which deals with design of circuits with solid state semiconducting devices, and it also analyzes electron movement in a semiconductor, conductor or gas. So basically electronics means you have to analyze the flow of charged particles, electron as well as lack of electron. Lack of electron will be called a hole, which is nothing but a concept. It does not exist physically, but it is absence of electron. So we have to analyze the movement of charged particles, electron and its opposite, that is hole, in semiconductor, conductor or gas. But most predominantly semiconductors are the elements which are used in electronics at a larger scale. So what may be the origin of this electronics? So you might be aware that in the era of Second World War, that is from 1939 to 45, European countries were using vacuum tubes for their warfare devices. And those vacuum tubes were very bulky, large size, and they were very noisy also. So you can see during that period, the vacuum tubes were used and they were having very large power loss, large size and low speed. Besides that, they were quite noisy. Noisy in the sense their output was not up to the mark. So people were in a search of a device which can switch quickly as well as the size may be small. So then Graham Bell Laboratory in USA came with an invention. There were three scientists, namely Dr. William Shockley, Dr. John Bardeen and Dr. Walter H. Brattain. You can see them on the screen. In the year 1947, at the end of 1947 and in the beginning of 48, they invented a device called a transistor, which was a semiconducting device. And afterward, electronics didn't look back. The revolution started with invention of a small transistor. The transistor that they invented was looking similar to this. What do you see? It is a replica of that first transistor. So it was much more smaller than the vacuum tubes that we saw in the first slide. These are the vacuum tubes, some of the vacuum tubes, triode, pentode, tetrode likewise. But due to their disadvantages, they were quickly replaced by the new invention called transistor in 1948 because it was published in 1948. So after that, the electronics revolution started and it continued up to this time also in 2020. So you can see the revolution path of electronics. Around 1950, single silicon transistor was having somewhat larger size than today's transistor. Then in 1960s, few transistors were combined and they were formed in the form of integrated circuit on a single silicon wafer. So you can see certain transistors were combined on a single silicon wafer. Then the progress continued. In 1970s, few microprocessors were invented on a single silicon chip with thousands of transistors. Around the 80s, the processor increased their capability and speed. They were 32-bit microprocessors and they were having lakhs of transistors on the same silicon chip. So it is called VLSI, very large scale integration technology, to form an integrated circuit with so many transistors on a single silicon wafer. In 90s, the progress continued and we were having high speed processors from various foundries, Intel and so on. In 2000, we were able to integrate tens of lakhs of transistors on a single silicon wafer. So you can imagine the complexity and small size towards which electron was heading. And what is the current situation? That we'll see later. But you can see these are the various transistors having three terminals, which is predominantly known as BJT. So now such discrete transistors were replaced by so many small transistors on a single silicon wafer. And current scenario is, this is the inner view of some integrated circuit on a magnified view. So right now many integrated circuit foundries are working in chip design, Intel, Micron, SMIC, etc. So their foundries are working present in the 2 to 5 nanometer wavelength. So right now you will not be in a position to understand what is this 2 to 5 nanometer wavelength of channel length. This is particularly a different transistors being used. They are MOSFET other than the earlier transistor, but they are named as transistor. So we can say very modification of transistor, a new transistor other than the earlier BJT are used. So you can imagine the small size, high speed, which is being expected in 5G technology right now. Recently, Apple launched iPhone 12 Pro with 5G features. OnePlus is also launching 8T with the same features. So you can imagine the hardware which is required for the same speed, which is nothing but based on these electronic integrated circuits. So you can imagine the miniaturization of these integrated circuits and use of electronics in this particular thing. So the electronic revolution has affected and will affect so many different fields. So as we talk of 2020 today, there are various fields in which require support of electronics, such as artificial intelligence, machine learning, robotic processing, edge computing, virtual reality, cyber security, blockchain, Internet of Things. So you might have heard such words, but their basic hardware will be electronic, and naturally this will all rely on the high speed small size design of electronic ICs. So this is the strength of electronics. So now, after defining electronics, that it is a branch of science and technology which deals with design of solid state semiconducting devices, we need to go into details that how does it differ from electrical, because both are almost similar, but electronics and electrical. So now we will discuss the difference between electronics and electrical. So in general, whenever the word electrical comes in your mind, you must be thinking about the power supply that comes to our home through various transmission lines. So generally we understand that electrical means electricity, and it is true also. But electrical as well as electronics both deal with electrons. But the difference is electrical combines different subparts, such as you can see electrical engineering involves study, design and applications of equipments, devices and systems involving electronics, electricity and electromagnetism. That means electrical is a wider field. It incorporates electronics also, power generation also and electromagnetism. So that means this electronics and electromagnetism are separated as a branch called electronics and communication. And electrical branch is now somewhat limited up to the power generation and distribution. So that means you can say electronics and electromagnetism deals with communication circuits, and that's why there is a separate field called electronics and communication. So in this context, we can say electrical is a parent branch. Electrical is a parent branch for all such branches such as EC, computer and information technology, because computer also depends on electronic hardware, which also is a basic part of electrical branch. So you can say electrical is a parent branch for all these branches. Now let's compare electrical with electronics. So I want to show you just different equipments which are electrical. So you can see on the screen there is a DC generator whose output will be DC voltage. You can see the size of such equipment. Next is a DC stepper motor. You might have seen such motors in various appliances of electrical. Next is transformer. It's not a small transformer, but it's a large transformer at power distribution, having primaries and secondary windings. Then there is an AC generator whose output will be AC voltage. So why I am showing this? Because I want to differentiate electrical and electronics. Next thing is induction motor, that is particularly an AC motor. You can see the size and material involved in such machines. Then there is a DC motor, earlier was a DC generator. Now look at the electronic or electronic components. The first and foremost which matters for you is a smartphone, a smart TV, or you can say desktop computer which looks like a smart TV, a laptop, a smart TV which incorporates so many features including Wi-Fi, cast screen and so many things, direct to home television systems, washing machines, audio systems which are particularly digital audio systems, LED displays and so many things which involves electronics. So after looking at all these applications of electrical and electronics, you can guess the difference between them. That these electronic devices deals with small power, very small power, but very high frequency. Whereas these electrical components deals with very high power but low frequency. Their maximum operating frequency will be 50 Hz in India for AC system, and for DC system it will be 0 Hz. But for electronics, if you talk about optical fiber, the operating frequency will be around 10 raised to 14 Hz. So that means let's notify the differences between electrical and electronics. So you can say, looking at their applications and their combinations, we can conclude that electrical deals with low frequency and high power applications. What do you mean by low frequency? So our line frequency is 50 Hz only. And do you mean by high powers? So the power generation may be in megawatt also using plasma generation. And what is the electronics then? Then electronics deals with high frequency up to terahertz, 10 raised to 14 hertz, and low power applications. Your mobile is charged with a 3.5 volt charger. So you can say power will be very less, up to few milliwatt only. So this is the main distinction between electrical and electronics. Electrical deals with high power and low frequency. Electronics deals with high frequency and low power. But most of the modern equipments uses combination of both. For example, a washing machine. Washing machine runs on electrical supply, but the control, the working, the operation is controlled by electronics and microprocessors. So that means most of the systems are having combination of electronics and electrical. But electrical will merely supply the energy, and the electronics will cause its operation, control, and variations. So this is all about comparison of electrical and electronics. Now what can be the types of electronics? That means classification of electronics. So you all have heard largely two words, that is analog and digital. So how they are differentiated? So based on the signals which they process, what is their input signal and what is their output signal? So based on input and output signals, or you can say information, the electronic circuits may be analog or digital. So we want to go in detail of this. For that we will again compare few practical aspects, then you will be able to differentiate between analog and digital. Just compare two things on the screen. On left side there is a wristwatch, which is a traditional wristwatch, and on the right side there is a smartwatch or digital smartwatch. You would say digital. Why it is digital we will discuss later, but this is one example. Now again compare, there are two televisions in front of you. On left hand side there is a cathode ray tube, picture tube television, which we were using before 10 to 15 years, almost 15 years back. Now nobody uses it. And on the right side there is a smart HD TV, high definition TV, having a flat screen, display will be LED. Nowadays iLED displays are available. Next thing that I want to compare is a tape recorder and a MP4 player of different company. Here it is of Sony MP4 player. Both are having same function. Both play songs, or you can say music. But this one is having different features and this one is also having different features. What are the different features that we will compare? So next thing is a camera. The earlier cameras, which we call traditional cameras or analog cameras, and look at the DSLR, which we use nowadays. Naturally advantages are so many, and why it is advantageous, that will be also known to you within few minutes. Just compare two kinds of displays are there. Now there is a speedometer of a vehicle or two-wheeler which shows you RPM, or you can say kilometers per hour, using a indication. And on the right side there is a straightforward digital display which tells you what is the direction, north or south, what is the RPM, and different aspects of the timing and rest of the things. So this is also a matter of comparison. So after looking at all these comparisons, what you come to know? Some of the applications are old as well as their output is not a unique one. Just look at the watch example. Suppose you are asked to find out time from this watch. Somebody would say it is 10 o'clock and 7 minutes. Somebody would say 10 o'clock and 8 minutes, looking at the display. So your answers may be one of infinite answers. Somebody would say it is 10 o'clock and 7 minutes 59 seconds. So likewise, your answers would vary. Your answer may be one of the infinite possible answers. While in this case, whenever you look at the output, there will be a single answer indicated by the device. A unique answer, a distinct answer. So that means your answer is one of the unique answer. As well, in this case, you get many possibilities of answer, possibly infinite possibilities. So this distinction makes them analog and digital. So let's go back. How do we define analog electronics and how do we define digital electronics? So what is analog electronics? The electronics which works with continuous value signals. The analog circuits which works with continuous value signals. Continuous in the sense their values will be a continuous range. So from a given range you can have any value. Then what is digital electronics? Which works with discrete value signals. That means you are dealing with distinct variable, or you can say distinct values, not so many values. So which makes a big distinction between analog and digital. In analog, there are possibly infinite answers. In digital, there are possibly finite answers. So which one is easy to use? Naturally, digital is very easy to use because you have to deal with finite values, and in this case you have to deal with infinite values. So this is one of the advantage. Later on you will come to know which are the other advantages of digital over analog. Now the question comes, if analog electronics works with analog signal, then what is an analog signal? For which I want to show you one exercise. Just look at the screen. You are having a periodical sine wave in front of you, and I am telling you that just divide this signal in equal horizontal parts. Equal horizontal parts. So that means, suppose somebody makes a line over here, and the line passes at suppose 4.5 volt, and someone else draws a line at a different point and the value passes at 3.5. Someone else makes a section at minus 2.5. Someone makes a section at minus 4. So that means between a positive peak and negative peak, which is finite thing, but the levels which you can draw will be infinite. That means between finite amplitude there are possibly infinite levels of amplitude. So it is quite interesting to know. Sine wave amplitude is finite, for example 5 and minus 5. So total amplitude is 10 volt peak to peak. But the levels of amplitude are infinite, which makes this signal analog. Let's go to the next signal. We have to do the same thing. We have to divide this signal horizontally in equal size part. So suppose you draw a line. So now when the line is crossing, suppose in this particular period, when line is within this period, what is the signal value? Signal value is high. When the line enters into this area, what is the signal value? 0, or you can say low. When the same line enters into this area, what is the signal level? High. When the line enters into this period, what is the signal level? 0, up to this. Here it is negative. So that means whenever you draw a line or wherever you draw the line, The signal shows only two levels, either high or low. That means this signal is having only two levels, or you can say finite levels. Whereas this signal, if you draw a line at anywhere, it will have different value. But in this case, wherever you draw a line, the amplitude indications will have only two values, either high and low. So that means the second signal is having finite levels of amplitude, and the first signal is having infinite levels of amplitude. Let's take another example. The signal in front of you is a random signal. You can see the amplitude varies, frequency varies. So if I tell you the same thing, you have to divide this signal in number of horizontal parts. So that means again the total amplitude is finite, but the levels of amplitude will be infinite. Suppose maximum value is 4 and minimum value is -2. So between them, if you draw number of levels, possibly they will be infinite. So the third signal is also having infinite levels. Now look at this signal. You have to do the same exercise if you cut them horizontally. So whenever the line is in this section, it has got 1 volt amplitude. When this is in this area, it is having -0.5. During this area, it is having +0.5. During this time, it is having -1. So that means wherever you draw a line, at any amplitude, if you draw a line, the amplitude will have only 4 levels: +1, +0.5, -0.5 and -1. That means levels of amplitudes are finite. So that means it simply says that this signal is having finite levels of amplitude. So let's go back to the first signal again, which is a periodic sine wave. What did I tell you? You have to cut this sine wave horizontally. Amplitude of sine wave is finite, you can measure it, but the levels of amplitudes are infinite. The second signal is a binary signal. Now I can say it is binary, but earlier you didn't know. So whenever you cut this signal horizontally, the amplitude levels will have only two answers, high and low. So it is having finite levels of amplitude. Look at the next signal, which is a random one. Again, if you cut it horizontally in number of levels, there are possibly infinite levels with a finite amplitude. And the last one, again, if you cut it at any point, you will get only 4 amplitude levels. So this is having finite levels of amplitude. So in any case, all the signals have got two options only. Either the levels of amplitudes are infinite, all the levels of amplitude are finite. So now it's easy to understand. The signal having infinite levels of amplitude is called an analog signal, and the signal having finite levels of amplitude is called a digital signal. So let's define them now. After defining what is analog electronics, which deals with analog signal, and what is digital electronics, which deals with digital signal, now let's define the signals, which you have already seen practically. What is an analog signal? The signal with infinite levels of amplitude is called an analog signal. Or you can say it alternatively. The signal which can take any value of amplitude from a given continuous range is called an analog signal. For example, in this sine wave, the range was 5 to -5. It is a continuous range, but you can take any value of amplitude between 5 to -5. That's why it is analog. What are the examples of analog signals? So interestingly, all sinusoidal signals, sine, cos, tan, cosec, sec, all sinusoidals are analog. Any triangular wave, sawtooth wave, all are analog signals because they can have infinite levels of amplitude. All random signals are also analog, and most particularly noise signal. Noise is a broad term which may be present in electronic systems also as well as mechanical systems also. But this is case of electronic system. So noise is also an analog signal because it can be of any value. It can take on any value. So basically, noise is an analog signal, which is undesirable. Now let's define a digital signal. The signal with finite levels of amplitude is called a digital signal, as you found in this square wave. It has got only two levels, high and low. So that's why it is digital. Or alternatively, you can say the signal which can take on only distinct value from given discrete range is called digital signal. Because between this positive and negative, there were only two answers, plus 5 and minus 5. You cannot take minus 3 as a value. You cannot take plus 3 as a value. That means you could take only a distinct value from a given discrete range. That's why it is called a digital signal. What are the examples? Binary signal that we saw, or you can say two-array signal. Binary means two, that is two-array signal. Octal signal having 8 levels. Hexadecimal signal having 16 levels. Or in general, you can have M-array signal. M may be 2, 3, 4, 5, 6, 7, 8, 9, whatever it may be. But if your number of amplitude levels are finite, your signal is said to be digital. So in general, people confuse themselves as binary is the only digital signal. No, binary is the basic digital signal. You can have number of levels. So if levels are finite, it will be called a digital signal. So let's conclude today's lecture. In today's session, we discussed about what is electronics, what it is, its history, how it is related with electrical, how it is different from electrical, what was the origin, what is the current status of electronics, which are the types of electronics, analog and digital, what is the difference in processing. So it will be quite fruitful for you. So the further topics about electronic devices we will discuss in the second lecture. Till then, have happy learning. See you in the next session.